Welcome back to Chapter 20. We're going to try to finish things off today with sections E and F, talking about the vertex of a parabola, which I briefly mentioned in the last video, as well as optimization, which is just a fancy type of word problem, and it's actually not even that fancy. So to begin, we talked about this previously. The vertex, sometimes called the turning point of a quadratic function or of a parabola, is it's going to be either the highest or the lowest point. It'll be the maximum point if the graph has this shape where it's opening downwards. It'll be the minimum point if the graph has this shape and it's opening upwards, corresponding to a positive a value in this case or a negative a value in this case. So here we have a quadratic function, and we're going to try to work out, without graphing it, what are the axes-intercepts, what's the axis of symmetry, what are the coordinates of the vertex, and then, using that information, sketch the function. So we're going to have a few different answers showing up on screen all at once here. Let's just focus right here. For the axes-intercepts, we know that to find the y-intercept, we're going to set x equal to 0. That's easy to do. I put it in here, and I get 3. Like we said in the previous video, since I have this in standard form, the y-intercept is always going to be the c value. So it's right there to begin with. And then to find the x-intercepts, we're going to set y equal to 0, giving us this quadratic equation to solve. In this case, it factors very nicely, so we get x equals 3 and negative 1. For the axis of symmetry of the parabola, that's always going to be negative b over 2a. So we look in the original equation, the a value is negative 1, the b value is 2, so negative 2 divided by negative 2 is 1. The axis of symmetry is x equals 1. What that tells us about the vertex is that its x-coordinate is going to be 1, because the axis of symmetry must pass through the vertex. Therefore, what we'll do is we'll set x equal to 1 here, and we'll get 4 as our y value, and that is the y value of the vertex, seen here. Finally, we sketch the function. So we plot the y-intercept, the two x-intercepts, the coordinates of the vertex. The book is also including the axis of symmetry. In general, if we're just sketching a parabola, I would not ask you to draw the axis of symmetry, but the book asked for it in this question, so we include it. All right, but anyway, that's how we can sketch a parabola if it's given to us in standard form. Now we're going to do the same thing for this equation, which is in factored form. I suppose you could multiply these three terms together to get an equation that's in standard form, and then you could follow the exact same procedure as what we did in the previous slide. But if you ask me, that's extra work. We don't have to do all that. We can just attack this problem directly from factored form. So we begin again with the axes-intercepts. Just like before, if we want to find the y-intercept, we're going to set x equal to 0. Now in this case, we actually have to do it. We don't see the y-intercept hanging out here as a constant, but when we put in 0 in here, we just get 2 times negative 2 times 4, and that's easy to see that it's going to be negative 16. Then to find the x-intercepts, well, yeah, we're going to set y equal to 0, but remember, since it's factored, I see the x-intercepts right away. We just set this factor equal to 0, so we get 2, and then this factor equal to 0, so we get negative 4. So since it's already factored, the x-intercepts are easy to work out. If we had multiplied through to get something in standard form, then we would need to either factor that or use completing the square or the quadratic formula. Anyway, the axis of symmetry. In this case, since we don't have a, b, and c, we're not going to use the negative b over 2a trick, but instead, the axis of symmetry is going to be in between the two x-intercepts. Our two x-intercepts were negative 4 and 2. So if we add them together, we get negative 2, and take half of that, we get negative 1. That's the average of 2 and negative 4, and that is the axis of symmetry. For the vertex, Again, this must be the x-coordinate of the vertex, so we put that in for x, and then we get the y-coordinate as negative 18. And then using all this information, we can sketch the graph. Again, the x-intercepts go in, the y-intercept goes in, the vertex is there. The book asked for the axis of symmetry, although I don't think it's necessary. Of course, some problems are a little bit more challenging, so here's an example of one of those. We can still work out all the important information, but as you'll see, it's just a little bit tougher. So this is in standard form. Let's say I want the x-intercepts. This does not factor. So unfortunately, that means I need to either solve a quadratic equation using completing the square or the quadratic formula. I prefer the quadratic formula. A is 3, B is -1, C is also -1. Put that in to negative B plus or minus the square root of B squared minus 4AC all over 2A. I get 1 plus or minus the square root of 13 over 6. Or, expressed as decimals, negative 0.434 or positive 0.768. Okay, I mean, it's annoying. We could do it. It's not too bad. The y-intercept, well, it's in standard form, so the y-intercept is always going to be easy. That's clearly -1. The axis of symmetry, it's also not too bad. If we just use negative b over 2a, that's going to be 1 divided by 6. So x equals 1/6. That's fine. And then we can use that to figure out the coordinates of the vertex. We put in 1/6 in for both of those x's. That's a little annoying, but, you know, squaring 1/6, that just gives you 1/36. This is all doable. You can get an exact value for the y-coordinate of the vertex. It's negative 13 over 12. Expressed as a decimal, the vertex is at 0.16 repeating, comma, negative 1.083 repeating. Okay, so really no matter what form your question is in, whether it's standard like this one, or factored, or vertex form, you can always get all of the information that you need about the parabola from the equation. Sometimes it's just more difficult than others. By the way, when we have difficult problems, we also have an additional tool at our disposal. So let's talk about calculators. So I've graphed the original function, and I just want to find out the important values, the axes-intercepts, and the coordinates of the vertex. So let's go to menu and analyze graph. Well, if I want to find the x-intercepts, I'm going to choose 0. Lower bound, I go to the left of the first one. Upper bound, I move to the right of the first one. There's my first answer. And then I do this a second time. I can't get them both at once. Anyway, there's my 2 x-intercepts. Now I want the y-intercept. Well, I mean, the quickest thing is really just to recognize that it has to be -1 from the equation, but I don't know if you didn't figure that out. The calculator can still get it to you. If you make a table, you can check there, scrolling up, when x is 0, y is -1. And then finally for the vertex, I can analyze graph. The vertex in this case is a minimum value, so I'll put my lower bound to the left of the minimum, scroll to the right, there is my minimum. And those values match what we saw on the previous screen. Section F is about optimization. Fancy word, it just means finding the least value, or the minimum, or the greatest value, or the maximum of a function. And actually we've talked about how to do this before using technology. Well, now that we're just dealing with a quadratic, we should be able to find, without using a calculator, we should be able to find the minimum or the maximum of any quadratic function, because it's just the vertex. Specifically, it's the y value of the vertex. So when we have word problems asking for a minimum or a maximum, it's just saying, find me the y value of the vertex. Let's take a look at one of those. So in this problem are 2 variables. They're not x and y, but they're t and h. All right, so h is the height at a particular point in time. And it doesn't matter that it's a rocket, it could be any object that's being launched into the air. It makes sense that we should have a parabola
with this basic shape, right? Something going up and then coming back down again. Also, I see when I look at the equation here that the a value is -5, so we should have a parabola that's opening downwards. Now, question A asks, how long does it take? So first of all, the answer that we're giving should be a t value, right? Since it's asking for a length of time. How long does it take for it to reach its maximum height? So this is an optimization problem. It's asking for us to find the vertex. And it doesn't really even matter where our parabola is, like if it starts at the origin or whether the starting value for the rocket is actually above ground. It really doesn't matter. In both cases, the amount of time starting at 0 that it's going to take to reach that maximum point is just going to be the x value of the vertex, or I guess the t value if you want to call it that in this case. So that's exactly what we're going to try to find. So we rewrite our function in kind of standard form, putting a in front of b. We know that the vertex is going to occur at -b over 2a. We can find out that that's 10, so we're going to reach the maximum height after 10 seconds. If you prefer, we could have also factored this. We see that the two x-intercepts are going to be 0 and 20, so the vertex should be in the middle of those two, which is at 10. So that also tells me that this graph is going to be the more accurate one. When t is equal to 0, my height is exactly 0. So the parabola is going through the origin. But anyway, they're not asking for that. They're asking now in part B to find the maximum height. So that's going to be the y value, or if you prefer, the h value of the vertex. So we're just going to put 10 into our equation and figure out what h of 10 is, and that is 500 meters. Okay, cool. And then letter C, okay, how long does it take for it to fall back to Earth? So now we're interested in the amount of time that it takes for it to go from the vertex down to the ground again. Now, since we're dealing with a picture like that, we know that the vertex is on the axis of symmetry. It's in the middle. So if it took us 10 seconds to get to the highest point, it's going to also take us 10 seconds to drop back down for a grand total of 20 seconds, which is the correct answer that we see here. It takes 20 seconds to get from launch to back on the ground again. However, if we had been dealing with an image like this one over here on the right, then we wouldn't have just been able to double the value. So I don't know, in this case, maybe this first value we found out was like 8, and then the distance to that next x-intercept was 10. Well, then the time taken would be, 18 seconds. So certainly, seek out shortcuts where they exist. There are, as we've seen, many problems in this chapter that can be answered in a long, complicated way or using a pretty fast shortcut way. But at the same time, don't invent a shortcut where there isn't one. All right, the vertex is in the middle of the graph. It's also in the middle of the x-intercepts. So just be careful and make sure that you actually have two x-intercepts, which in this particular case we wouldn't have. So that is all the important stuff that there is to know about the graphs of a quadratic function. What we have not yet discussed is how to go from a graph or a table of values back to the associated quadratic equation or quadratic function that would produce those. So I am going to put out one more video, chapter 20 plus, that will explain how to do that.